So thank you for the kind introduction. Yeah, I want to talk today about how UV imprinting can be used to make micro-optical elements that can have some function in automotive lighting. So I'm from DELO, so who's DELO? Well, we are a family-owned company. We have about 230 million turnover per year, and we are close to 1,100 employees now. So we are a company focusing on materials. So our main business is on adhesives, but also on other kind of polymers like imprint resins. Besides that, we also develop and manufacture equipment for dispensing or for curing. So when we talk about UV imprint technology, for us it's basically four areas where we think this technology can really have a big benefit, and that's augmented reality, optical sensing, automotive lighting, and imaging. And if we look a bit more closely to that, of course, for augmented reality, it's mainly the waveguides that can be made by using nano-imprint technology. For optical sensing, it's diffractive optical elements as one example. For imaging, you can build a full optic stacks with one or two free lenses with apertures all done on wafer level and very small, probably just 1 millimeter or even smaller for a camera. And what I want to talk today is automotive lighting, projector or headlamp applications using MLAs. So like what has been presented before. In this case, basically all what is depicted in magenta here is where polymer materials could be used. We've seen this. Applications of such MLAs could be just decorative use for light carpets. It could be to project some safety signs, but it's also used in headlamps. I would call everything a projection system. I mean, it's pretty clear for the images shown in the lower part, but if you think about it on a conceptual view, a headlamp is nothing but a projection system. It projects light to the environment. So, why should you consider micro-optics big? And well, first let's look how a projection system is working for centuries now. You have a slide, the slide is illuminated, and then you have a lens to project the image of that slide to some screen. So that works perfectly, but that's the bad thing about it. Well, the bad thing about it is that in optics, almost everything scales. So it means you have a small screen, you don't need too much light, then you can go with a small system. You have a large screen, you need a lot of light, you need to get to large lenses, large distances, all that. And there's not so much you can do about this. And the bad thing is, for a car, you always have a big screen. If you think about that light carpet, the screen is the road. If you think about headlamps, the screen is the whole scenery. So that's the reason why the headlamps nowadays are really quite bulky. And of course, you all know micro-optics can have a solution there, and that's the old solution, divide and conquer. So basically, you take the one big slide and the one big lens and divide this into many small slides, many lenses, so you have many projection systems, and you nicely calculate and do the overlap and all the alignment, and then you can come up with a much smaller system. So how is that realized? Well, that's depicted here. So we have basically a micro lens array. We have so you have here the projection lenses. You have a slide basically encoded here in the control data. That gives you the patterns, and then you project it. Well, materials provided by us can be used to make this micro lenses. Let's just a quick overview on the process. So you have the glass plate with the chromium patterns on it. When you do a dispense of the transparent polymer, you bring in to contact a stamp which has cavities everywhere you want to have the lenses later on. When you do the UV cure, you remove the stamp and you end up with an MLA on your glass. So we have developed some materials that can be used as the imprint material for this MLA. But of course you also know the system is more complex. You need an LED, you need some heat sink, you need a collimating lens, all that. Being an adhesive company, we can of course also offer the adhesives for the bonding applications. But today I really like to focus on the imprint materials to making this micro lenses. And we are talking about automotive, and in automotive, reliability is really essential. I mean, you buy your car and you expect it to work for the next 10, 15, probably 20 years. So reliability really matters. But what does reliability mean? Well, the answer is not that easy. There are many aspects, and basically, depending on which application you're looking at, there's a slight difference. And I want to talk today about some selected topics on that. So if we go throughout the process, first you do the imprint, then you have some additional process, and then the main thing, of course, on reliability is during operation. And basically during all these steps there are somehow different requirements on reliability. So if we talk about the imprint process, you want to get a reliable imprint. It means you want to get a perfect copy of the lenses. You want easy clamp separation, things like that. Downstream process, you might have some anti-reflection coating, some dicing, some handling. Again, you want the material to behave in a reliable way. And during operation, of course, it's topics like yellowing, dimensional stability, adhesion or mechanical stability, and especially in that last point during operation, you have external and internal factors acting on that material, so, such as temperature, humidity, radiation, or temperature shock. And today I picked 3 of them, and let's start with the imprintability of the lens. Well, if you want to characterize a lens, you need to measure it. And that's something we've done there. And I mean, being into optics, it's really a bad thing, but one of the best ways to measure a lens is still by tactile system to scratch over it to really get a very precise profile of the lens shape. And if you want to characterize a spheric lens and you only want to get 2 parameters, it's probably you measure the radius of curvature and you measure the conic constant. And in fact, that's something we've done here for one combination of imprint material and stamp. And what we do is we start with imprint number 1, and then we do a series of 25 imprints, and then we see, okay, that's not really a reliable process. It's the first lens looks pretty different from the lens number 25, so from the 25th imprint, and clearly that's nothing you want. So we need to tweak our imprint material, we need to tweak our stamp material, we probably need to tweak the process, and we can see that you can get a much better control, and now it's really a good imprint quality. Yellowing or transmission. Well, I would say it's not that difficult to make an UV curing epoxy material that has nice transmission over the full visible wavelength range. But when things start to get a bit complicated is when you put these lenses went to high temperature. Good. So when you put this lenses or these MLAs into the oven at 125 degrees C for up to 1,000 hours, and when something that is really a meaningful test for an automotive headlamp, you see the transmission drops. Material starts to yellow, and clearly that's not what you want. So we had a really hard time to optimize the materials, and now we could come up with materials that basically have no change of transmission even after 1,000 hours stored at 125 degrees C. And the last thing I wanted to talk about is mechanical stability, or the stability under temperature cycling. And if you think on a very abstract way on how your MLA looks, it's a layer of polymer, which is depicted in magenta here, on a glass in blue. If you look at the system at 23 degrees C, room temperature, everything is nice, perfect. But what happens if you heat it up, you switch on your headlamp, you heat it up to 20 degrees C. Well, of course, there's some thermal expansion, and the bad thing is the polymer has higher thermal expansion than a glass. So the material wants to expand, but it's stuck, it adheres to the glass, so there's quite some stress built up at the interface between polymer and glass. Basically the same thing, but opposite direction happens if you pull it down to -40 degrees C. The polymer wants to contract more than the glass. Again, you build up stress. And now think you're doing this not just one time, but you're doing this 100, 500 times. So you're always putting stress in your system, and well, that's happened if you have not carefully optimized your material for this application. Then you will get some cracking, some delamination. You might even get cracking in the glass. So we've observed this because the material sticks pretty much to the glass, but it cracks the glass. If you tweak the material's properties, you'll find a solution where you can withstand this harsh test. We've tested 500 cycles, we've even tested 1,000 cycles, and it works. So, but you need to optimize and balance Young's modulus, glass transition temperature, CTE, all that kind. Okay, how's that going on? So we have materials that work right now, but of course there's a trend making everything smaller. The LEDs will get more powerful. You want more miniaturization, so the LEDs will get closer to the MLAs. So there's a lot going on there, and for us as a material supplier, this means we need to constantly work on all materials and do some reformulations to make them even more reliable. Well, and now I'm basically at the end, so I talked about 3 aspects on reliability, 3 aspects on the material. Of course, there are much more aspects that are relevant if you design a material. There's the optical properties, there's the processing that needs to work. We need to have the mechanical properties right, all that reliability stuff. And that's also the reason why there is not a one-fits-all material. But it really depends on what is your application, what is your geometry, and that's just basically what I want to encourage you. If you have a need for some material, please come to us, talk to us, and we can try to find the best solution for your application. That's the end. Thank you.
Thank you, Markus.